Hey, Katie.
Hey, Ben. What you been up to lately?
I've been spending a lot of time on YouTube, actually.
Mm.
There are a lot of good YouTube videos on different topics,
Mm-hmm.
music, also data science. Yeah, have you been spending any time on YouTube recently?
I wouldn't say I've been watching more YouTube than usual or anything, but I have been reading about it a little bit, and that's kind of what we'll talk about today.
All right. You were listening to Linear Digressions. So, is reading YouTube a thing, then?
I think reading papers about YouTube, it's fair to say that that's a thing. I'm not aware of anyone who... I know people who listen to music on YouTube. I know people who learn how to do stuff on YouTube. I'm not sure I know very many people who just read on YouTube, though.
Yeah. So, wait, what is it that you were reading?
Right. So I was reading about a system that they have built over there called Procella. I believe I am pronouncing that correctly.
Procella, like Coachella?
Yeah. No, it's spelled slightly differently. Procella.
Okay.
Anywho, yeah. So this is the data system that they have set up to power 4 different types of analytics use cases, which I think is really interesting because usually what you would do if you have 4 different types of analytics use cases, you would have 4 different systems and you'd be shuttling data back and forth. But instead what they've done at YouTube is they've built one unified system. And so Procella is the name of that system. I was reading sort of a white paper that describes how it works and why they made some of the design choices they did.
One system to rule them all.
That is the goal. That is the goal.
Right.
So let's start with what are the different use cases that you want to enable. So this is all under the bucket of analytics data serving. So if you've been listening to some of our other more recent episodes, you know that there's also another high profile use for databases, which is sort of transaction handling for running applications. We're not talking about that stuff by and large. Instead, this is just data that's being used for various analytics needs. And those 4 needs are, number 1, this is the data that powers reporting and dashboarding. So imagine that you are, for example, a creator or sort of like a video author or something on YouTube. You have, some reports and some dashboards and stuff like that you can log into to see how many views your videos are getting and that sort of thing.
Right. So I guess that data has to come from somewhere, and normally you would build a system just to handle that data.
Right. Yeah. So in that case, let's talk about each of these. What are the needs of each of these systems as we go through them? So for reporting and dashboarding, because we are doing that on roughly the scale of, maybe the number of creators or the number of videos, that's a very high volume of data and of queries that you have to be able to serve, because there's potentially, the entire user base of YouTube might be interacting with that data. These people have probably an expectation that the data is pretty fresh. So if someone watched a video of mine 10 minutes ago, I want to see that reflected in my report or my dashboard. So being able to see things, I don't know, maybe not necessarily in real time, but pretty fast after they happen.
Yeah. I mean, like, if you launch a video, you want to get a pulse on how well it's doing. Let's say if you get 10 million views roughly on a video, and you launch a video, you're going to get a lot of views really quickly, and your dashboard shouldn't say 0 views for 5 hours.
Right. So you want to be able to access fresh data, and you want to do it with a fast response time. So I don't want to log into my dashboard, have it run a query, and then it has to wait 30 seconds or a minute or, who knows, multiple minutes for it to return something back to me.
I definitely have had that experience on some websites where most of the pages on the website or web app or service are fast, and then you go to the charts view or the analytics view, and you see a lot of spinners as these things happen in the background.
Yeah. So that's not a good user experience. Yeah. So the second use case is embedded statistics. So this is when you're actually in the application. There's, this little ticker that says how many times a video has been viewed, how many thumbs up it's gotten, how many thumbs down. Yeah.
So statistics that are actually embedded in the user experience. So you're not going to a stats view, but you're just clicking around YouTube and you see these statistics that are maybe a little bit more general or rougher in the actual user interface.
Yeah, and so those are, I guess that's a little bit starting to flirt with something that looks more application-based, but it's analytics because it's looking at potentially all of the data that's in the database to try to be able to compute those numbers. So this is also a pretty large volume of queries that you have to be able to handle. They say on the order of millions of queries per second, because I guess that's probably roughly the order of how, the frequency with which videos are viewed, which is probably what's driving most of that.
God, it's insane. It reminds me of how big the world is.
And moreover, you have also the need here to have a low latency or a fast response time. You don't want to have this query waiting for a long time for you to get this number to show up in YouTube, or heaven forbid that it would actually hold up the video from playing because it's busy fetching some metadata about how many people have already seen this video. So that is the second case, embedded statistics. Number 3 is monitoring. So the first two, the reporting and dashboarding, embedded statistics, those are kind of external facing analytics calculations. Monitoring is a little bit more internal. So these are metrics that mostly engineers at Google are paying attention to because they want to monitor how well the system is performing and know if there are any trouble spots that they need to be paying attention to.
Yeah, if you see a spike in a certain metric, then, maybe that means something's wrong. If all of a sudden all of your video views for a particular video go to 0, that probably also means something is wrong.
Yeah, so you want those to obviously be looking at more or less the same data that's powering the other use cases. And so this is a lower query volume. You're not necessarily going to be computing this millions of times per second. But these are probably slightly more complex queries than what you might have for your average external facing cases. And in particular, they probably have some slightly different needs. Like, how many times has this video been viewed? You can imagine there's probably some optimizations you can make there to make that very, very fast. But for something like monitoring, you might want to say something like, how many times has this video been viewed in the last hour relative to the previous 30 days, except if it's younger than 30 days, in which case, maybe go find some reference video, so you have the idea of there's data that's kind of falling off the tail end of that as it ages out of the window. There's choices that maybe you're making about which data sources you want to query so that you get the freshest stuff. So lower volume, but kind of higher complexity. So that's the monitoring case. And then the last one is also more internal facing than external. This is ad hoc analysis. These are probably the queries that are being done by the data scientists or maybe product managers, those types of business folks, business analysts, those types of people who are trying to answer questions like, what's our number one video overall this week? Or how is the overall number of minutes spent viewing YouTube videos stacking up this week relative to the same week last year?
Yeah, or like, what's the distribution of age ranges of users watching educational videos or something? Yeah,
so this is, again, relatively low volume because there aren't tons of people, there are maybe hundreds of, or at max, I would imagine thousands of people who are running these queries, which is still plenty, but, compared to the total number of people who watch YouTube videos, relatively small. So low volume. This is a case where moderate latency is okay. So if it takes a minute for one of these queries to finish, that might be the end of the world, or it might not be the end of the world, rather. But there's a pretty high complexity that sometimes these would take because you're potentially looking at many different tables across the whole system, and there's very low predictability about what people might want to analyze. And last, kind of related perhaps to that high complexity and low predictability, is the potential that these queries have to go over enormous volumes of data. So to do a query like, I don't know, an unoptimized version of a query like, what is the most viewed YouTube video of all time? You could imagine it has to query the entire database of all of the viewing data, which is huge. Now, I'm sure they have a shortcut for something like that because it's probably those types of metrics are maybe a little bit more optimized. But you can imagine that it's conceivable that the entire volume of the data might be something that you need to query for these kinds of calculations. And
Right.
so it needs to be able to handle that.
So those are very different use cases, and they built one system to handle those different use cases?
Yeah, and I hear a little bit of skepticism in your voice.
Yeah, that seems a little crazy to me.
Say a little more about that.
Especially for those first two cases, you need to think very carefully about the way that you build and optimize your system in order to get the low latency. Especially for, like, a dashboard, you don't want to have latency, but it's okay if you have some. But you certainly want to have as close to zero latency as possible for something like embedded statistics use cases, because you don't want the viewing of a video to be held up by checking to see what the video count is. Like, that's kind of insane. So I guess I would imagine that since you have such different use cases and such different needs in terms of how you optimize and how you arrange your data, and perhaps also differences in the way that you choose to organize your data over time. Like, maybe you decide to move around the way some database is stored in order to, I don't know, work better with a particular use case that's new. It seems like you get a lot of benefit from separating out your systems, because then you don't have as much to keep in mind when you make changes or optimizations.
Yeah, I think that's a great point, and that's certainly my instinct. Like, if I were I'm not a data engineer, but if I were a data engineer or kind of a data engineering adjacent data scientist, and someone were to come up to me with these 4 use cases and says, should we build one system for this? Or maybe we don't need 4, but let's say more than 1 at least. What would be my instinct? My instinct would be to go with more than 1, because exactly like you say, they have very different needs, and usually what you would do is you would use different technologies that are optimized for different needs. So a valid question is, why do this? And that's something that they talk about in the white paper that I was reading. And in short, it's because it's the lesser of two evils in this particular case. So as you can imagine, the volume of YouTube data is very, very large. And so you can imagine that if you need to have multiple systems that are all more or less consistent with each other, that, like, ideally they're perfectly consistent with each other. So the numbers that you get querying the data from one system in one way give you the same numbers as querying, hypothetically the same data in another system. Like, as an example, we said reporting and dashboarding, something that I might be using as a creator to see how many views my video is getting. There's also, for embedded statistics, there's a little counter of how many views a video has gotten that gets served up that way. So if those two numbers aren't the same, then I'm going to have some questions, right? So you want it to be consistent, which means that you have to be shipping data back and forth constantly in order to keep that synchronization up. And they were finding that the maintenance burden around those ETL pipelines was really significant. There were a couple other problems that they cited as well, that even the systems that they were using were starting to break down because of the huge volumes of data some of them were handling, that moreover, having different systems that have kind of different rules of engagement was a lot of mental overhead for the people who had to hop between the different systems, but these people instead want to just have one system to rule them all. Like I said, lesser of two evils, but it means that then there's a lot of interesting complexity that Procella has to have to elegantly handle all of these very different use cases.
That all makes a lot of sense. So basically, you're saying instead of maintaining multiple systems, as well as the overhead of understanding multiple systems that you might need to use, you make one system that's more complicated and maybe a little bit more difficult if you work on it, because you're maintaining the overhead of thinking about all of your different use cases. But it might be easier for the consumers if that system is good.
Yep. Yeah, that's right. So let's talk about a few of the technical details. We'll include a link to the white paper on lineardigressions.com so you can read about all of the ins and outs that they've documented. We'll get through a few of them here, though, that I thought were kind of interesting. First is that you have a very large system with a huge amount of data in it and all different kinds of complex or not so complex queries that you need to run on that with different latencies and different volumes. We already talked about all that. What this suggests is that, for starters, you want to split storage and compute, or that was the decision they made, to split where the data is stored and the file system in which the file storage happens from the place where they actually do the computes, the calculations on the data. So Colossus is the name of their file storage system, and then Borg is their parallel compute system. These are both, I think, somewhat general to maybe to Google, maybe not even just to YouTube. But the point is that you want to have storage decoupled from compute so that one can scale without the other, and it can flex kind of vertically and horizontally at the same time.
Okay, that makes sense, yeah.
Yeah. So a second important split that they have to satisfy is there's two different types of data that you want to be able to deal with in a system like this. So one is what they call real time, or sometimes this is called like streaming or online, versus batch or offline data storage. And so roughly the split here, for people who aren't familiar with these terms, is that if you're YouTube, there's kind of the historical look back, all the data that's in the tank already from all of the historical usage that you have, everything up until 30 seconds ago maybe. So that's obviously getting bigger every second that goes by because time is ticking forward and there's more data to add sort of into that repository. But at the same time, for certain monitoring cases or for certain things that have to update very, very quickly, there isn't enough time for the data to get into that permanent storage, batch storage, in order to be queried up quickly enough for the use case that you have. So you also have all the data that's coming in, the streaming data or the real-time data, as it's more or less as it's being generated. So if you want to think in like not very good analogies, imagine that the, Colossus, the big data storage system, is like a swimming pool and the water is the data. And then there's also like a fire hose that's just pumping more and more water into the swimming pool. So for certain types of queries, you want to be able to query the swimming pool. For other types of queries, you also need to be able to query the fire hose because it takes a little while once it gets into the swimming pool for it to be queryable that way. Does that make sense?
Right. Yeah, well, kind of. I would have gone with a lake and a river because you can't really expand or scale a swimming pool while water is in it.
Good point.
I get your point.
Yeah. Okay, so that's one of the interesting things that you can see in sort of the architecture diagram of this whole system, is that at the foundation is this file storage system, Colossus, but there's a split fairly early on between queries that can go through the batch system, like I only need to be able to look at historical data, versus queries that need to access the streaming data, the stuff that's more or less happening in real time. For example, monitoring is probably something that needs to have access to very, very fresh data. And so that would need to go through potentially both systems in order to serve up numbers that are correct.
Right, because it needs to look at what's happening now, but it also might need to look at historical records to get kind of a baseline to compare against.
Yeah, and so a brief digression that I actually want to make on this, I'm taking the paper slightly out of order now, but I think it's interesting and it's worth thinking about, is that, so there's a lot of optimizations that they made around how to store and access the data once it's in the file system. And what that means is that when the data goes into that permanent storage system, there's some computation and some processing that happens on it. When it's coming in from the pipeline, it's still in a fairly raw format. So you can imagine that there's some work that needs to happen between the, the streaming system and the storage system. It's like, imagine that you had, I don't know, some kind of filtering appendage thing that you put onto your fire hose or your river or whatever that does some stuff to the water before it's allowed to go into the swimming pool or the lake.
Right.
Yeah. And so a lot of, what are they doing? They're doing things like calculating summary statistics on that data. They are registering it in their metadata management system. They're compressing it. And so when you have to make use of the real-time data system, you can imagine that there's some optimizations that have to be handled relatively high up about which parts of a query they're going to send through the real-time system for something that's a little bit more raw, and that, maybe there's a smaller volume of data that has to be taken out of that system. Hopefully that's true, because hopefully you're getting most of the data from the batch system that has all of these compressions and optimizations and metadata management registries all applied and whatnot. But it's kind of interesting because ultimately the two systems have to interact with each other at the data storage level. And so I think that's a thing that's easy to take for granted, but isn't totally obvious, is sort of like, where are the seams between these two systems when you are writing queries that are potentially interacting with both of them at the same time?
That's a fascinating problem to, I don't know, I guess to try to grok and then to try to solve.
Right?
Yeah. And I imagine that as a user of the system, you probably don't need to think too hard about this. Maybe you have to decide whether you want the fire hose or the swimming pool or both. But in terms of like, I'm guessing how you structure your query, probably a lot of the behind the scenes stuff is abstracted away from you.
Yeah,
so you just kind of say like, hey, I want this data, and give it to me, and then the entire system that you're querying against does a whole bunch of work that you don't even need to be aware of.
Yeah, I think that's totally right. So let me describe what happens when you put a query into this system as a user. What system does it then pass through? So exactly like you said, I, as a user, probably don't want to have to think about the complexities of whether this needs to access this real-time system or the batch system. I just want the data that I have, and I want the system to figure out where it needs to go get it without me having to tell it any of that stuff. Like, I shouldn't have to worry about that. So I'm in my query client and I type in a query like, get me this data, maybe with like a where clause that puts some limits on it, and maybe I'm calculating some statistics like the mean or the count or something. So what happens then is that query goes to what's called the root server for parsing. So the root server is kind of like the first destination that's doing actually a whole lot of stuff, and we're gonna skip over a lot of it. But some of what it's doing is kind of the breaking down the query and optimizing it. It's figuring out what the data is that I'm asking for, and then the next thing that it does is it goes to what they call the metadata server. Let's assume that I'm working mostly through the batch system, which I think is mostly the case. So the metadata server is think of it as kind of like it's not exactly a data dictionary, but that's not too bad of an analogy. It's keeping a bunch of metadata about the data itself, like
metadata is data about data.
About data,
like,
yeah.
If you have a file, metadata would be what time was this file created, when was it last modified, what file type is it, that kind of stuff. And so metadata does not just apply in a file system like on your computer. It applies in any case where you've got some stuff, and then you need to know some higher level, more general stuff about the data itself.
Yeah, so in this case, the metadata server is storing a few types of information, I think. So one is a general map to where the data is located. Like, I want data that's in this table. Well, actually, under the hood, all the data is stored in files. It's not stored in tables. So it needs to know what file it's on, and it needs to know what computer to go talk to because the file lives on that computer, and all these kinds of things. But there's also a lot of the most common access patterns, it sounds like, have been pushed to metadata as well. So if I want to say something like, what is the total number of rows in this table? I don't know. Let me just pick as a simple example. Like, let's say that's a usage pattern that is so heavily trod that instead of going to the table itself many, many times and just computing that over and over again, instead, that number gets pushed to the metadata layer, so I just have to go retrieve it. I don't actually have to go to the data itself. And so there's a whole lot of higher level kind of summary data that gets pushed to the metadata layer. So for certain types of queries, that's actually, I think, where I can stop. And so then when new data gets in, like we were talking a little bit about how it comes in through this real-time pipeline, and then it goes to what's called the ingestion server, which is, I think, updating things like the metadata, then that's what sort of keeps all of that stuff in sync. So I go to the metadata server, figure out maybe I can get the answer to my question. Maybe that's just going to tell me where I can go find the data itself. And then there's a next level, which is called the data server, which actually deals with the data itself if need be. So this is reading data into memory. This is doing actually, the calculations on that data. Remember, this is kind of, I think, where Borg starts to come in, doing the actual compute. At this point, I'm actually a few layers deep in the system. I'm very close to where the data is actually being stored. I'm not far away from it at all. And this is following another, kind of general best practice around this type of thing, which is push the calculation as close to the data as possible. We want to send the query to the data rather than pulling the data through multiple computers to where the query lives, because moving around data is pretty expensive.
It's really interesting to think about the way such a large service would have to handle things like this. I mean, like, I don't know the exact statistics, but I think on the order of several years of video are watched every second, just because there's so many people watching videos on YouTube.
Yeah, and I think in the interest of time, we'll probably start winding this down, but there's a whole bunch of, you can imagine, other types of optimizations that they made that you can read about in the paper. So this is things like, how does their caching system work so that they can minimize the amount of data that they need to, load into the cache, or there's a whole custom-built columnar storage format that they made for this. Or how do they make sure to, well, they don't really say how they do this. They just mention that they do it, but they do this thing called affinity scheduling. So trying to keep the same metadata on the same server so that you don't have to load it in and out of caches. I think it's a really interesting paper to try to read through, and to, you won't be able to implement this on your own just from a 7-page write-up or whatever, but it gives you a nice description of, some of the overall trade-offs and optimizations they had to make. And the last thing I'll say about it is it ends with some nice performance descriptions of the system, which, if you're not a person who interacts with these systems that much, it gives you a little bit of an idea of how they're evaluated and what some of the timescales are, or data volumes, or those kinds of metrics for a system like this. So you get an idea for each of the 4 use cases of what are some of the performance metrics that they have, and how well does the system perform at a few key benchmark points.
That's awesome. So if anyone is listening to this podcast, any startup founders who are looking to, disrupt YouTube, this paper would be a good place to start.
Well, let me actually, if you're a startup founder, what you need to do these 4 things. You should just use 4 different systems. Yeah.
Never mind.
No, I think it's fine. No, it's a good point though. This is always the gotcha about papers that come out of Google, where Google is like, I'm lumping YouTube in with Google here, right? But like, Google is like, here is how we solved this Google problem, because almost nobody except Google is Google. So if you're trying to solve got a 5 gigabyte database that you need to serve, and you're doing it in Procella, then you're probably doing something wrong. Yeah. But all that aside, if you're at Google and you don't know about it, this is how YouTube works.
Engineer, and you need to,
yeah. Or let me put it this way: if you next time you're on YouTube and you see that little counter thing, or if you're a content creator on YouTube and you're looking at your dashboard, like, this is the system that's powering all this stuff. It's pretty complicated, but it's pretty cool.
Linear Digressions is a Creative Commons endeavor, which means you can share or use it any way you like. Just tell them we said hi. To find out more about this or any other episode of Linear Digressions, go to lineardigressions.com. And if you like this podcast, go ahead and leave us a review on iTunes so other people get to listen to this content too. You can always get in touch with either of us. Our emails are ben@lineardigressions.com and katie@lineardigressions.com in case you have comments or suggestions for future shows. You can tweet us at lindigressions. Thank you for joining us, and we'll see you next time.